So at this point, we've given an algorithm for a problem we've been wondering about for a while, finding the basis for the null space of a matrix. Given the matrix, we think of it in terms of rows, and we find the orthogonal complement of the span of the rows in Rn, where n is the number of columns. And to do that, we let E1 through En denote, as usual, the standard basis vectors for Rn. And we find the non-zero vectors among the output of orthogonalize with the input list A1 through Am followed by E1 through En. Here's another approach to finding a basis for the null space of a matrix. This time, we'll write the matrix in terms of its columns. Now, here's the equation that relates the original vectors supplied to orthogonalize to the output vectors. The original vectors form a matrix. It's equal to the matrix formed by the output vectors times this matrix. This is an invertible matrix, so we can move it to the other side, and we get this equation that expresses the starred vectors, the output vectors, in terms of the original vectors. I'll illustrate the algorithm through an example. Suppose we supply the vectors v0 through v6 to orthogonalize, and it outputs the vectors v0 star through v6 star. So this is the relation between them. The matrix consisting of the input vectors is the product of the matrix consisting of the output vectors times this invertible matrix. We can move the invertible matrix to the other side, multiplying by its inverse. And now, suppose as before that v2 star, v4 star, and v5 star are zero vectors. These are zero vectors. Okay, so the corresponding columns of the triangular matrix are these. Now, it's clear that these are linearly independent vectors. And notice that by the matrix vector definition of matrix-matrix multiplication, when you multiply this original matrix by each of these vectors, you get a zero vector. So these vectors lie in the null space of this matrix. They're linearly independent, so they span a space of dimension 0. And the rank nullity theorem shows that the null space of this matrix is exactly 0 because the non-zero vectors in the output form a basis, and there are 1, 2, 3, 4 of them. So the columns that we've identified are indeed a basis for the null space of this matrix. So let's review the algorithm. To find the null space of a matrix, we apply orthogonalize to the columns of that matrix and find the upper triangular matrix T such that the original matrix equals the matrix whose columns are the output vectors times the triangular matrix. Then we take the inverse of the triangular matrix and return exactly those columns of the inverse that correspond to the zero vectors among the output vectors of orthogonalize. So this algorithm raises two questions: how to find this triangular matrix T and how to find its inverse. First, we'll address finding the matrix T. We'll write a procedure I call augmented orthogonalize that takes a v-list, say v1 through vn of vectors, and outputs, as before, the vectors v1 star through vn star that are mutually orthogonal, and also some other vectors r1 through rn. These have the property that the matrix formed by the original vectors equals the matrix formed by the star vectors times the matrix formed by r1 through rn. The procedure is based on our orthogonalized procedure together with augmented project orthogonal. So here's the procedure. It very much resembles orthogonalize. It uses rvex to accumulate these r vectors. instead of calling project orthogonal, it calls augmented project orthogonal, which returns not just a V star vector, but also the corresponding column of the R's, represented as a dictionary. And the procedure just packages that dictionary up into a vec and returns in the end the list of starred vectors and the list of R vectors. Using augmented orthogonalized, we can fill out this procedure a bit. So we use augmented orthogonalize on the columns of A, and we get back a list of starred vectors and a list of R vectors. We let T be the matrix whose columns are these vectors in R vecs. And then we return the columns of T inverse corresponding to those vectors in V star list that are 0 vectors. Well, how do we find a column of T inverse? From our knowledge of matrix inverse, we know that T times T inverse is the identity matrix. So we can find column J of T inverse by solving an equation, T times the unknown column, which we call X, equals the corresponding column of the identity matrix, which is the standard vector. And how do we solve this equation? We can use triangular solve because T is a triangular matrix.